Have you ever stopped to think about what's actually going on inside your phone or your computer? I mean, what's the magic that makes it all work? Well, today we're diving into the unsung hero of all modern technology, the semiconductor. It's the tiny, powerful brain inside pretty much everything you own. All right, so here's how we're going to break this down. First, we'll look at the fundamental problem of controlling electricity. Then we'll go on the hunt for the perfect material to solve it. And after that, we'll uncover the incredibly clever hack that transforms this material into the foundation of our entire digital world. Let's get into it. So here's the thing. If you want to build anything smart, anything with a computer chip in it, you've got to be the master of electricity. You need to control its flow with absolute precision. But our most basic options, well, they're kind of terrible for this. One is just total chaos, and the other is a complete dead end. Neither one gives us the fine-tuned control we desperately need. I mean, it seems simple enough, right? You've got materials that let electricity flow freely, and you've got materials that stop it cold. Conductors and insulators. On and off. What else could you possibly need? Well, it turns out you need something that's not just on or off, but something you can tweak, something you can control. Think about it like this. A conductor, like a copper wire, is basically a wide-open fire hose for electrons. They're just gushing everywhere, totally uncontrollable. And an insulator, like rubber, that's a pipe that's been welded shut. Nothing gets through ever. Neither of those is very useful for building something complex and, well, smart. So the hunt was on for something in the middle. Not an open fire hose, not a sealed pipe, but something with a valve we could control. And you know where scientists found the answer? In a kind of overlooked spot on the periodic table. It all comes down to the magic number 4. The elements in this particular group have 4 electrons in their outermost shell. Now, what's so special about that? It gives them this incredible flexibility. They can either give away those 4 electrons, or they can grab 4 more to feel stable. They're not committed one way or the other, which is exactly the kind of potential we're looking for. Okay, so we've got our group of candidates, but we can narrow it down pretty quick. Carbon? It's way too much of a wild card. It forms all these different kinds of bonds and structures. I mean, think about the difference between a diamond and a lump of coal. Too unpredictable. And the heavier elements down at the bottom, they're unstable, radioactive, definitely a no-go. So, after the dust settles, we're left with 2 solid contenders, silicon and germanium. So, silicon. It seemed perfect. But then, a huge roadblock. You see, when you have a crystal of pure silicon, it's too perfect. Every single atom bonds perfectly with its 4 neighbors. They share all their electrons, so there's nothing left to move around. No free electrons means no electrical current can flow. It's a perfect insulator, a total dead end, or so it seems. So what do you do when perfection is actually the problem? You mess it up on purpose. And this is where the real genius of the whole thing comes in. It's this brilliant, completely counterintuitive hack called doping. Doping is the secret sauce. It's the whole key to this thing. We're talking about deliberately and very carefully introducing tiny impurities into that perfectly useless silicon crystal. And it's this controlled contamination that finally gives us the power to tell the silicon what to do. And we can do this in 2 different flavors. On one hand, you can sneak in an element that has 5 outer electrons. 4 of them bond with the silicon like normal, but that leaves 1 extra electron just kind of hanging out, free to move around. We call this N-type for negative. On the other hand, you can add an impurity that only has 3 outer electrons. Now you've got a gap, a spot where an electron should be. We call this a hole, and we call the material P-type for positive. All right, this is it. This is the moment where everything comes together. We've got our N-type silicon loaded with extra electrons. We've got our P-type silicon full of these little electron-sized holes. So, what do you think happens when we stick them right next to each other? The second they touch, there's a rush. The free electrons from the N side see all those empty holes on the P side, and they just flood across the border to fill them in. But here's the catch. As the N side loses those negative electrons, it's left with an overall positive charge. And the P side, by gaining all those electrons, now has a negative charge. This creates this really interesting charged barrier right at the junction where they meet. And that barrier has a name, the depletion region. You can think of it as a natural, self-forming wall. It's an electrical field that's now strong enough to stop any more electrons from making that jump across. So it's like a gate that has slammed shut, all by itself. Okay, so we've built this automatic gate that shuts itself. That's kind of neat, but not super useful unless we can figure out how to open and close it whenever we want. And we can. All it takes is a little push from an external voltage. We call this biasing. And this part is just brilliant. If you hook up a battery so the positive end connects to the p-type side and the negative end to the n-type, you're basically pushing the electrons and holes towards that middle barrier. And that depletion region, it shrinks down to almost nothing. The gate opens and current flows. But if you flip the battery around, now you're pulling everything away from the junction. The depletion region gets wider and wider, the gate slams shut even harder, and no current gets through. It is a perfect one-way street for electricity. And I'm not talking about a small difference here. Look at this. When you have it in forward bias, the current flows like it's on a freeway. But when you put it in reverse bias, the flow drops to basically zero. It's an absolute brick wall. We have built the perfect one-way valve for electricity. And just like that, we've done it. We've created a perfect, controllable one-way switch for electricity. It seems so simple, but this little device, this PN junction diode, is literally the fundamental building block of our entire digital age. So we have this tiny one-way switch. How on earth does that get us from here to supercomputers and smartphones? Well, let's look at its first killer application. Okay, so let's talk about power. The electricity coming out of the wall socket in your house is alternating current, AC. It's constantly flipping back and forth. But your electronics, your phone, your laptop, they need a steady one-way stream called direct current, or DC. So you need something to make that conversion. And that something is called a rectifier. And how does it work? It's just our little one-way gate in action. Think of the diode as a bouncer at a club. The AC current comes along with its positive and negative waves. When the positive wave comes through, flowing in the right direction, the bouncer opens the door. Forward bias. Current passes. But when the negative wave comes along, trying to go backwards, the bouncer slams the door shut. Reverse bias. Blocked. What you're left with is just the positive pulses. You've chopped the AC wave in half, creating a current that only flows one way. And that is the magic inside every single charger you own. But it doesn't stop there. This simple one-way gate is like the ultimate Lego brick of electronics. Put them together one way, you get rectifiers. Tweak the design a bit, and they release light. That's an LED. Another variation can turn light into electricity. That's a solar cell. And most important of all, if you sandwich them together in just the right way, you create the transistor, the microscopic switch that is the beating heart of every single computer on the planet. So when you look at your phone or your computer, just remember what's inside. Billions and billions of these tiny one-way gates, all working together, all made possible because someone figured out how to make a perfect crystal just a little bit imperfect. It really makes you wonder, doesn't it? What will they enable next?